Here's question number 5. It's one of the short FRQs. In this case, it's one page. It wouldn't be any more than 2 pages. And scanning it over, you can see we have an A, B, C, I, and a C, I, I. So there's only 4 parts to this. So each part's only worth 1 point. So don't spend too much time on any one of these, because you know you're only going to get 1 point for each of these. Okay, let's start the question. FRQ, question number 5. We've got a table with elements and their first ionization energies in joules per mole. You can see 4.95 times 10 to the 5. Rather than using kilojoules, they use this scientific notation. The first ionization energies of Na, sodium, and potassium are given in the table above. Sodium metal reacts vigorously with water to form a hydrogen gas and a metal hydroxide. Okay, information. Potassium reacts vigorously as well, but bursts into a violet-colored flame. Here's a quick video to show what the sodium and potassium look like when they are put into a flame. The cotton swab has some sodium chloride on it, and the Bunsen burners can provide enough heat to take the outer electrons of sodium and potassium and excite them. And then when they drop back down, they release photons. In this case, you can see the brilliant orange that sodium produces. It's very, very bright, and if you had anything else there, you wouldn't see it. Potassium's flame color is a bit more subtle and not nearly as bright as the sodium. Here you can see it's a nice violet. Now that you've seen the flame colors, let's answer the question. Write the electron configuration for a potassium ion. Fortunately, with the FRQs, you don't have to page forward to look at a periodic table or an equation sheet. You'll find that when you get your FRQ, you'll get a free response booklet that you'll fill in and answer the questions for, but you'll also have an orange reference booklet, and that reference booklet will have the periodic table and the equation you'll need to answer some of these questions. So you can have that right next to you as you're writing the answers on your free response question. The Section 2 FRQ Orange Reference Booklet. You won't have that, unfortunately, with the MCs. So you could go to that orange reference booklet and find that potassium element is in the 4th period, and knowing how to use the periodic table to determine the electron configuration, you could figure out, we'll start with a 1s and fill that up so that we've got a 1s2. And then, of course, we go to the 2nd period where we have a total of 8 electrons, a 2s2 and a 2p6. We have our 3rd period that we go to, 3s2, 3p6, and then after going through the 3p6, we now are in the 4th period, and we stop with the potassium in the 4s1. However, you've got to be careful if you answer this quickly. Indeed, this is a beautiful electron configuration for potassium. This says potassium plus 1 ion. The graders wanted to see if you knew that a plus charge would mean 1 less electron, and that you would end up just giving it this electron configuration, the 1s2, 2s2, 2p6, 3s2, 3p6, which is the electron configuration of argon, which is the same as the potassium plus 1 ion. There we've got that answered. Now there is another possibility that you could have used. You could have written the abbreviated electron configuration, and if you'd have done that, you would have taken the noble gas argon and put a 4s1 on it, because that was the one after that. But again, this is our ion, so you'd have to get rid of that 4s1. And you couldn't just write argon. You'd have to go through and use the noble gas neon and then do the 3s2, 3p6. They would not accept argon as the abbreviated configuration. Sometimes they won't allow an abbreviated configuration. They'll say the complete electron configuration, but if they don't say anything specific, then you can use the abbreviated if you like. But I really advise using the full electron configuration. Now, a word of caution, this was not a transition metal. If you run into the transition metals, you'll have to remember that the 4s fills before the 3d does. But I very, very strongly advise that you reshuffle things and put the electrons in their actual energy levels. This method of having the 3D after the 4s2, the Aufbau, quickly, it's a learning technique. The actual energy levels are the 3Ds are below the 4s. And if they would ask you for an ionization, you remove these valence electrons, the 4s, not the 3D. You remove the 4s before you do the 3D. There's been a number of AP questions where you had to know that the 4s ionizes before the third energy level D. So we've got A taken care of very nicely. We've figured out the configuration for the potassium ion, and I gave you a couple of warnings about some other things too. Well, with 1 point for getting correct electron configuration, we're ready to go on to the second point. Based on the principles of atomic structure, explain why the first ionization energy of potassium is lower than the first ionization energy of sodium. Word of caution on this. Here we've got sodium and potassium. One of the things that readers say is that students will talk about trends on the periodic table just based on location. A typical answer, the student would say, as you go down the periodic table, ionization energies decrease. That is not an explanation. That just tells you something about the periodic table. It doesn't explain why. When you have an explain, you really have to tell what is the cause of what's happening. You have to explain the chemistry, not just a periodic table trend. So it's important that you indicate why that electron is more easily ionized. Well, I hope you remember and know that the valence electron of potassium is at a higher principal energy level. This extra row, this fourth row, is because we have a new energy level that is farther from the nucleus. That valence electron, therefore, is easier to remove than the valence electron in the lower principal energy level. That's all that was required to answer this. That was the explanation using the principles of atomic structure. Now, if they would have said Coulombic forces, then you'd say as electrons are further away from an atom, there is a lower electronic attraction. You could have said that here too, but you didn't need to. That was all that was needed. So don't say, oh, this atom is smaller because it's to the right on the periodic table. No, you have to explain what chemistry is behind it. There's our second point. And with 2 points, you get more than the global average. And we still have C with I and II. So let's get those next. And you'll find some special tips on how to answer question I and II at my YouTube channel, Mr. Muskluck AP Chemistry, underneath the playlist AP18 FRQ Test Preparation.